Okay, so yesterday we talked about reflection. And at the beginning of the lesson, I mentioned that when light hits a boundary, or when EMR moves in a straight line, and when it encounters a boundary between mediums, some of the electromagnetic radiation is reflected, which you saw with the lenses. Some of it, like when you shone it at 20 degrees, you should have seen a reflected ray back at 20 degrees. And some of it is refracted, which means it moves into the new medium, but it moves at a different angle. Like it bends. And it bends because it's moving at a different speed. That's called refraction. Okay? So refraction is it describes how the movement of wave changes when it enters a different medium. The speed of EMR is greatest in a vacuum. That's when it's 3.00 times 10 to the 8 meters per second. When that EMR enters any other substance, water, glass, diamond, oil, tar, anything, it moves at a different speed. It slows down. Okay, so its speed is less in a substance which is more optically dense. So more optically dense means that it's kind of thicker. I don't know how to describe that, but it's like water is more optically dense than air. Glass is more optically dense than water. Plastic or acrylic that you have is more optically dense than water and then air. Okay. So we have this thing here. If we are going from air into water, my normal line kind of disappeared, but it is there. So that's my normal line. Okay. And again, if I have an incident ray coming in, then I'm going to have a reflected ray coming out at the same angle. Right? These angles will be the same. That's the angle of incidence. This is the angle of reflection. Okay. Okay, angle of incidence, angle of reflection. So remember, angle of incidence equals angle of reflection. So then this is the incoming or incident EMR, reflected EMR, and then this would be the refracted EMR. And you should have noticed when you were working with both the water and the lens, that when you shone it through the laser through at 10 degrees, the angle that it came out of the water, the lens at, was less than 10 degrees, or the angle got less. It moves, in other words, that angle of incidence, it gets closer to the normal line. When we're talking about refraction, instead of using I and R, because we use that for reflection, when we're talking about refraction, we use 1 and 2. So this would be theta 1, and this would be theta 2. Okay. So theta 1 is the incident angle, and theta 2 is the refracted angle. Okay, and this is the refracted angle. Air is more refractive. Sorry, less refractive is the one that's here. Let's try that again. Less refractive. It has a refractive index of 1.00. That's on your formula sheet. Water, and we'll talk about what a refractive index is in a minute. Water is more refractive, which means it causes a greater bending of light than air does. It has a refractive index of 1.33. So I have this as going as the incident EMR. So this is going from water into air. So that's what we would say here. This is, or sorry, air into water is what we have here. when you're looking at it from this way. You could also flip this over and think of it the other way, even though the arrowheads are all pointing like that it's going from air into water. But if I have a incident ray here going from water into air, notice that it bends away from the normal, because that means it's going slower here and then it's going faster here. It's speeding up as it goes into air. And I know some of you guys tried that. You kind of went the other way through the tank. So when light slows down, it bends towards the normal line. So that means it's going from a less refractive index to a more refractive, less refractive medium to a more refractive. When light speeds up, it bends away from the normal line. So this is slowing down, bending towards the normal line. Going this way would be speeding up, it bends away from the normal line. That means it's going from a more refractive medium to a less refractive medium. So these numbers that I've written here, these N1s and N2s, these are called indexes of refraction, or indices, I guess is the plural. Every substance has a unique optical density. Okay, so every substance has its own unique optical density. And that optical density is represented by something called the index of refraction. It's just a number, it has no units. Okay, it's signified by the variable n, and it has no units. It's like it's like a ratio. If you remember when we did coefficient of friction in physics 20, that was a ratio of the normal force to the force of friction, and the index of refraction is a ratio of the optical density of one substance to another substance. Really, like a one substance to air is what we're looking at. So the index of refraction for a vacuum is 1. Okay, and we are not in a vacuum. A vacuum would be space. We're not in a vacuum, but air, Earth's atmosphere, is close enough to a vacuum in terms of numbers that we still use it, right? Because the speed of light at being at 3.00 times 10 to the 8 meters per second, that's in a vacuum. That's really in a vacuum. But the difference between the speed in air and the speed in a vacuum are decimal places that we don't see when we round to 3 sigmas anyway. So then the index of refraction of air is 1.0003. But we say n air equals 1.00. And that is on your formula sheet. Okay, that's the only one that's on there. That's you don't have to memorize indices of refraction. You're either solving for them or you will get them in a question. And this is just repeating what I said at the bottom of the previous page here. Movement from a high index medium into a low index medium causes light to be refracted away from the normal, so speeding up. So that's like going from water to air, acrylic to air, acrylic. I always want to put an extra R in there. Acrylic to air, going from acrylic to water. Awesome. So that means it bends. It's going to bend away from the normal line. Okay. Movement from a low index medium into a high index medium causes the light to be refracted towards the normal line. It slows down. And so examples there are air into water, air to diamond, and so on. And then, water to acrylic. We did it that way. Acrylic. I guess I say the word wrong. And a Dutch physicist with probably the coolest but weirdest name I've ever seen, Willebrord Snell. He worked with refraction. He found a relationship between wave speed, direction, wavelength, and index. By direction, that means angle. Okay, and that is what's called Snell's law. Okay, and it's kind of a crazy looking formula. It's V1 over V2 equals lambda 1 over lambda 2 equals sine theta 1 over sine theta 2 equals n2 over n1. And yes, the n's are supposed to be 2 over 1, where everything else is 1 over 2. And what all the variables are in here is, one is the incident medium, or the from. Two is the refracted medium, or the two, right? So when I'm saying from air to water, air would be 1 and water would be 2. Then V, of course, is speed in meters per second. Lambda is wavelength in meters. Theta is the angle in degrees. And N is the index of refraction. And when you're doing this, you're going to use only 2 ratios at a time. It's not possible to solve something with 3 equal signs in it. So maybe you're just using speed and wavelength, or speed and angle, or angle and index of refraction. You're picking the 2 given the information that you have in the problem that you've been given. And that is on your formula sheet, so you don't have to memorize that. And there's actually kind of, what I think is a funny story behind this is they revamped the physics data booklet about 4 years ago, and they had that formula wrong. And it took about 6 weeks into the year to figure it out. They had it at N1 over N2, so nothing was right. But that's the formula the way it's supposed to be. Okay, and so this is not actually a difficult formula to use at all. This is actually kind of one of the easier things I think in this unit is the refraction stuff compared to when we start to get to refraction in thin lenses, like in the formulas we have to use for talking about images that are formed in thin lenses, which we'll start tomorrow. So we want to find the speed of light in water. To do this, now, and that seems like there's not much going on there. So you can do 2 things. You can use air as 1 and water as 2, or you can do it the other way. It doesn't actually matter which way you do it because that formula is just fractions, and whether you do it, whether you pick your 2 to be one thing and your from to be another thing, or you do it the other way around, you're still going to end up with the same answer. So there's the only place where you can make a mistake in doing that is when we talk about total internal reflection. There's sort of an internal way of checking that then too. So I'm going to make air 1 and water 2. So then my N1 is 1.00. My V1 is 3.00 times 10 to the 8 meters per second. And my N2 is 1.33, and I'm looking for V2. So I pick from my formula, I'm going to do N2 over N1 equals V1 over V2. And however you want to do this, whether you want to rearrange first and then plug it in, or plug it in and then rearrange, what you're doing is cross multiplying and dividing. So V2 is going to be N1 V1 over N2. So 1.00 times 3.00 times 10 to the 8 meters per second. The only place you can really make a mistake in this, like you want to keep your 1s consistent and your 2s consistent, right? So 1 is always air, 2 is always water in this example. The place where you can make a mistake, I suppose, is rearranging. That's the most likely place to make a mistake, is not cross multiplying and dividing correctly, but most of us remember how to do that because that's something we've been doing for a few years. Yeah. Oh, because I meant to put the 1.33. My fault. Okay. Thank you. Any questions so far about that? Seems pretty straightforward, not too difficult. Okay, so what basically happens is that when all you're given is a single piece of information about one medium. Like, so in the first one it was water, and the second one now we're talking about glass, and you're given no information about the other medium, then just use air, because we have all that we need for air except the instant angle, and that doesn't matter if you're dealing with angles and you're going to be given them. But we know the speed of light in air, we know the refractive index of light in air, and in some cases, like if we will never have to find out specific wavelengths, but we could, right? Because we know wavelengths of different colors of light. So find the index of refraction of a piece of glass if its speed of light in the glass is 2.15 times 10 to the 8 meters per second. So I'm going to make one air. Actually, I'm going to do it the other way, just to show you that it works to go backwards too. I'm going to make two air and one glass. So N2 is 1.00. We're looking for N1. V2 is 3.00 times 10 to the 8 meters per second. And V1, we're told, is 2.15 times 10 to the 8 meters per second. So we're using the same relationship we used up top, N2 over N1 equals V1 over V2, and we want to find N1. So 1.0 over N1 equals 2.15 times 10 to the 8 meters per second divided by 3.00 times 10 to the 8 meters per second. And then you can just go right to your answer if you want. You don't actually have to show me the rearranging part. I'll put it in here just so that you can tell if you've done it right. Yep, 1.40. So whether you chose to make air 2 and glass 1 or air 1 and glass 2, you're going to get the same answer. You guys try example 3. You guys cheat. And you're aiming for, you should get 25.6 degrees. Make sure your calculator's going to be pretty low for this. And if you've forgotten, the way to find an angle is inverse sine. Okay, moving on to the next one here. Green light of wavelength 545 nanometers enters a transparent liquid from air with an angle of incidence of 72 degrees. Inside the liquid, the angle of refraction is 50 degrees. What is the resulting wavelength? So we have, it enters liquid from air. So 1 is going to be air and 2 will be the liquid. So N1, oh wait, we don't need the index of refraction anyway. Lambda 1 is 545 times 10 to the negative 9 meters, right? Nano is times 10 to the negative 9. Theta 1 is 72 degrees, and theta 2 is 50 degrees. And we're trying to find lambda 2. So lambda 1 over lambda 2 equals sine theta 1 over sine theta 2. So lambda 2 is lambda 1 times sine theta 2 over sine theta 1. So 545 times 10 to the negative 9 meters times sine of 50 degrees divided by sine of 72 degrees. When you're doing this, putting it in, be very careful with the brackets. Because notice how when you type in sine 50 degrees, a bracket comes, when you type in sine, an open bracket comes up. You need to type in 50 and then put the closed bracket, or else you're going to end up with the wrong answer. It'll take the sine of everything that comes after it. So that'll give you 4.39 times 10 to the negative 7 meters, which you can also write as 439 nanometers, because we tend to write the wavelengths of light in nanometers. And you don't want to say theoretically or technically, that like 545 is green light, 439 is violet light. So in actual fact, the color will change. The color of the light will change. It's just very, very hard to see. You have to have very, very specific conditions and a very, very specific kind of laser to actually witness that. But it will. Okay, it will change. There is, if I had the right equipment, and I'm still trying to kind of put that together, because I just finished reading an article about it, but I haven't had the chance to put all the equipment together, but I'm trying. So we're going to weekend and see if we can get it together. It might not be, it's not going to be as obvious as we want it to be, but you should be able to see it. It usually has to do with, and I don't know actually what it is. I don't think that works though. But it's you have to use a particular kind of oil. I don't know. I think olive oil works. I just haven't tried it. So that's green. It actually to me looks yellow inside. Can you see it is yellow inside? Yeah. Yeah, okay. Yep. It's purple. So it's kind of blue inside. So yeah, it does work. Yeah. Remember how to press the oil? Clearly, look at that. And the red doesn't change. But it has to be something with a much lower wavelength for it to change. So that's actually really cool. This is violet, goes white, and this is green, which goes yellow. Okay. Okay. So find the angle of incidence in water with this setup. Okay. So we have like going from water into air. We're given the indices of refraction of each one, and we're given the angle. We're given theta 2. We want to find theta 1. So N2 over N1 equals sine theta 1 over sine theta 2. 1.00 over 1.33 equals sine theta 1 over sine 55 degrees. So theta 1 is inverse sine of 1.00 times sine 55 degrees divided by 1.33. You should get 38 degrees. Okay, so now what I want to talk about is total. Did everybody get the right answer to that one? Because anybody having any issues? Tyler, did you figure out the one that you did before? Did you get it right again? Did you? Because it's air, it's air. Because the speed of light inside air. Yeah. And you can look at it like this, say going from glass to air or going from air to glass. That's why it's okay, so total internal reflection is what we name the phenomenon that happens when the angle of incidence is so large that all of the light, what would be the refracted light, actually gets trapped in the new medium and can't get out. Okay, so you saw that when you went from the D lens into water, it happened at somewhere between about 65 and 75 degrees, right? And it can only happen, this is really important here, it can only happen, and this is sort of the internal check, and I'll show you what I mean by this. It only occurs when the incident ray comes from within a medium with a higher index of refraction. So it's going from a higher index to a lower index. So it only occurs if N1 is greater than N2. Okay, so going from a D lens into water. Going from water into air. Going from diamond into air. And this is why diamonds sparkle. Diamonds have an extremely high index of refraction. Their index of refraction is one of the highest ones known as 2.42. Okay, so that is why and this isn't really too much of a reflection, but I got a pre-design on the ceiling anyway. But what happens is light gets into diamond and a lot of it can't get back out again. So it gets trapped inside the diamond, and that's what makes it sparkle. But again, I'm going to sound like Sean from Spence, who I really hate, but the way the diamond is cut has an impact on that, right? The way the faces, the facets of the diamond have to do with that. And the new commercial is doing really annoys me because they're claiming that John Steinbeck says it's okay to go into depth by a brain. I've always had an issue with the fact that men are expected to have a little diamond ring, but what is the woman by the man? You know, so we're all into gender equality, but then we want to have a big fat diamond. I think, in all honesty, guys, buy your wife a house. That's gonna get you that way better. Anyway, that's my 2 cents. I'll shut up. But anyway, because purple's going to be harder to see because it's lighter. Okay. Can I make a what? Disco ball. No, but I can give you a disco effect here too. Also, because what's happening here? What's happening is when you hit some critical angle, all of the light reflects back into the initial medium. So let me actually draw a diagram first, and I'm going to do a couple more demos that sort of illustrate the diagram. So if we can draw on here our boundary and our normal line. So this will be the boundary. This is the normal. Okay, so this is the high index. So N1, which is a higher index, and then N2 will be a lower index. So examples of that, it might be, let's say, diamond to air. What happens then is if your angle of incidence is large enough, okay, so it has to be a fairly large angle of incidence, and that large angle of incidence, in order for total internal reflection to occur, that's called the critical angle, so theta c. So the critical angle is the incident angle that results in an angle of refraction that's equal to 90 degrees. So what's actually happening is there's no refraction down here, it's just refracting right at 90 degrees. Okay, so it's sort of staying trapped in there. So if I was to draw an arrow, and I'll have to make it a different color for it to show up, but it basically comes along that line. Okay. So it's everything is and then we call it total internal reflection because it looks like all the light is just reflected back. There's no actual refraction happening. So the critical angle results in theta 2 being equal to 90 degrees. And so then at and beyond this critical angle, all of the light reflects back into the initial medium. Okay? And I said before, this is the sort of the physics behind fiber optic cables. It's what makes a fiber optic cable work. And this is meant to represent a fiber optic cable, though it's much bigger, but it's basically like meant to be the same thing. And what happens here if I shine, which one do I have? I want the green. If I shine my laser light into the end of it, none of the light's going to come out. It just stays inside. Okay, and so you can see it, like you might see the end reflecting up there. But what's happening is that where the light hits the acrylic, the side of the acrylic, it's always at an angle that's big enough to be at or beyond the critical angle, so all the light just reflects back in the medium, and it just keeps going around like that. Okay. It's like, what? The internet?
Or, I don't know what to call it.
Fiber optic cables. And the lenses and binoculars use this as well. That I don't have anywhere near as good of a grasp on how that works. Then there's this other cool thing I can show you, which I call my light sight. Okay, and this, if you've never seen Niagara Falls, well, you're going to see basically the coolest thing about Niagara Falls. Apart from the fact that you can pay $16 to go and get a mist, it's fun, but disturbed me was all the people with their iPads out, and I'm like, yeah, that was weird. Maybe not so much. And then I went to fly, and it was like about 36 degrees, and where those really funny. So now, due to the lovely quality of the water coming out of our tap, I have to let it sit a little bit. Mike, I'll drink this. Yeah, I know. Okay, so you have to let me know if you're seeing something kind of cool here, because I can't actually see because I need to concentrate on the sun. No, not yet. No, I've got my finger over a hole, and I've got to shine the laser out on the hole. The water's going to come. You guys come. Don't stand next to, like, be careful that you don't, like, because the laser, well, it actually should come out. It's just if I miss something.
Didn't shower.
Another example. Now we can. Well, listen to that. Everybody have to go pee in a few minutes. Hey, so you have this critical angle, right? And what I've said is that when you're at or beyond that critical angle, all of the light reflects back into the initial medium because it has an angle of refraction equal to 90 degrees. So then the relationship that you use to deal with critical angle is then sine theta 1 over sine theta 2 equals n2 over n1. Okay? Where theta 1 is your critical angle, is theta c. Theta 2 is 90 degrees, and sine of 90 degrees is just 1. And n2 must be smaller than n1 for it to work. And that's because when this actually simplifies, what you get is sine theta critical is equal to n2 over n1. And this relationship has to be true because you cannot find a sine theta has to be between -1 and 1. It can't ever be bigger than 1. So if you have the bigger number on top and the smaller on the bottom, it's wrong. Okay, and you're getting an error message. So you're getting, like your calculator is telling you you're not doing this right, and then just flip it the other way. So this is not on your formula sheet. Okay, so this is not on your formula sheet like this. It's a simple formula to memorize. It's also a simple formula to figure out from this relationship here. And so we'll just do a couple examples of critical angle. So find the critical angle for water to air. So you're always having to go from a higher index to a lower index. So this is N1, which is 1.33, and this is N2, which is 1.00. And I kind of broke my rule there, and I haven't told you the index of refraction in water, but we had it from earlier examples. So yeah, I would never give you a question where you have to actually look it up. And we want to find the critical angle. So critical angle is inverse sine of N2 over N1, which is equal to the inverse sine of 1.00 over 1.33. And you can try it as inverse sine 1.33 over 1.00 to see that you get an error. And that's going to give you 49 degrees there. So that means that at 49 degrees, an angle is bigger than 49 degrees. All of the light trying to leave water to into air is trapped in the water. So that was what that angle that was coming out at there was at least 49 degrees. Like not the angle it's coming out at, but the angle that the light was hitting the water at when it started to bend. Okay, so you guys try example 7 there. I'll tell you what angle you should get, but it's exactly the same setup as example 6. Just make sure the smaller numbers on top, bigger numbers on the bottom. And you should be you're aiming for a critical angle equal to 61 degrees.